Let's do another example. This time we'll use sine of e to the x on -5 to 2.3. Don't worry that doesn't make any sense. We'll see it kind of makes sense later. So step 0, do not graph. Remember, we're trying to do this by symbolic logic. Step 1, what is f prime? So go ahead and take the derivative of sine e to the x. All right, hopefully you got derivative of sine is cosine. And then we have to multiply by the derivative of the inside because of the chain rule. And the derivative of e to the x is e to the x. So we have cosine e to the x times e to the x. Step 2, set the derivative equal to 0, and solve. So where is cosine e to the x times e to the x equal to 0? Wow, that looks complicated. I'm not going to be able to use the quadratic formula or anything like that. What we need to use is the principle that if a product is 0, then either one or the other or both of the factors have to be equal to 0. The only way to get 0 by multiplying is to have a 0 as one of the two things you're multiplying by. So if a product is 0, or in this case, is to be 0, at least one of the factors must be 0. So then we can simplify this to not the product, but where is cosine e to the x 0, where is e to the x 0. Let's handle the second one first. Where is e to the x equal to 0? Well, let's graph e to the x. Looks like that. It's never equal to 0. So we'll never get a 0 here by having e to the x equal to 0. Let's do the other part. Where is cosine e to the x equal to 0? You could try taking arc cosine or something, but I think a graphical approach will be handy here. Let's just think, how does cosine of t look? Let's draw cosine of t. Looks like that, and again. And where are the graph? So I'm not saying this is x, this is t, just thinking plain old cosine. Where is cosine equal to 0? Well, right here, and that's at t equals pi over 2. Right here, t equals 3 pi over 2. Right here, 5 pi over 2. Here again, 7 pi over 2. And also back here at negative pi over 2, negative 3 pi over 2, etc. So those are all the values of t where cosine t equals 0, but we need x where cosine e to the x is equal to 0. So let's pick the first one, the first crossing there. So we're saying where is basically cosine e to the x, or cosine t equal to 0 at t equals pi over 2. So that's saying that e to the x equals pi over 2. So what value of x makes that equal to e to the x equal to pi over 2? You could say we'll take the log of both sides. So you could say log e to the x equals log pi over 2. Log of e to the x is just x, that's why we did the log. So x equals log pi over 2. Log pi over 2, let me take a look, is 0.45 or so. All right, so this crossing gives us, when we map it to x, gives us a cosine of e to the x that's 0. How about 3 pi over 2? So we'd say similarly, x equals log 3 pi over 2, all the same logic as before, which is about 1.55-ish. X equals log 5 pi over 2, which is about 2.06-ish. So we could keep going that way. Actually, what about 7 pi over 2? That turns out to be bigger than 2.3 here, so it's outside the interval we want. Anything else we need to consider? Well, cosine is 0 here at negative pi over 2. What x value gives us that? So we'll say, what about t equals negative pi over 2? Would you say x equals log of negative pi over 2? Well, you can't take log of negative values, so that's just nothing, no solution. And similarly with negative 3 pi over 2. Okay, so altogether, what values are we getting for where the derivative is 0? We are getting log of pi over 2, log of 3 pi over 2, log of 5 pi over 2, log of 7 pi over 2, but that's outside our interval, and that's pretty much it. Okay, so that was all to answer where is the derivative 0. Step 3 is where does the derivative not exist? Thinking about sharp corners, or the function runs off to infinity or something, but within a finite space. But this is cosine e to the x. Everything is smooth and continuous. So not a problem, because f prime, which is cosine e to the x, is continuous. We'll talk more about what continuous means later, but for right now, it doesn't have any jumps or breaks in it. All right, so our critical values are log of pi over 2, log of 3 pi over 2, log of 5 pi over 2. Let's turn the page. All right, our steps 4 and 5 are computing y values. We might as well do those all kind of in one big table. And we might as well have Desmos compute that, so let's switch to Desmos. All right, here we are. We typed in the original function. We never verified that our derivative was right, but here's the our by hand derivative, and here's Desmos's difference quotient derivative, so that seems like everything's working okay. And here's our start and stop. Here's a table of our starting place, the 3 critical values that we got, and the ending place. And we can plot those here. So what's our global minimum? What's our global maximum? Well, here's our global minimum. That's the smallest of all the values in the table. That's this one. Our global maximum is this one and that one. You might say, well, what if there's a tie? Does that mean neither one wins? Well, remember we said the definition of global min or global max is something that is as good as or better than. For a global max, it would be as high as or higher than any other point. Here they're tied, so they both count as global maxes. So that's this one and that one. And then our endpoints, let's unlabel those. Our endpoints are just kind of in the middle in terms of y values, so they're not maxes or mins in particular. And now that we've done all that, we can graph the function itself. And we were going from -5 to 2.3, 2.3 being, oh, actually right there, our endpoint. So we found the global maxes and the global min, and then the endpoints weren't anything particular. Do you remember what the name of this kind of function is, where the frequency of the sine wave is getting higher and higher as we go along? It's a chirp. All right. It's kind of interesting that when we did the critical values, we were just saying where is the derivative equal to 0, and we didn't have any idea at that point really which ones were going to end up being a min or a max. We could see the cosine going through 0 one way or the other, but it wasn't clear until we actually did this. Later in Chapter 3, we'll think about ways to detect whether something's going to be a min or a max based on the behavior of the derivative at that point.